Hi, good afternoon, everyone. So, in today's lab, we are going to work with Y type circuits as well as the delta type circuits. So, what we're going to do actually is we'll build a circuit with, where the resistors are connected in a Y network fashion, and we are going to connect a load resistance, building that circuit in LTSpice. This is our circuit. So we'll build the circuit in LTSpice and we will find out the power dissipated by this load resistance RL, and we'll also find out the voltage across this resistor. During the next step, we are going to convert this Y network into the delta fashion. So once we connect this into the delta fashion, we'll connect the load resistance again, and we will verify if the power dissipated and the voltage across the resistor remains the same. We are not going to stop over there. What we're going to do next is to find the Thevenin equivalent of this very circuit. So we'll find the Thevenin equivalent circuit, and once we're done with finding the Thevenin voltage and the Thevenin resistance, then we'll connect the load resistance again, and we are again going to test the circuit for the voltage and the power rating. Once that's completed, the next step is very similar. We'll just find out quickly the Norton equivalent of the circuit, and we'll connect the circuit in the Norton network fashion, and we'll verify the power dissipated by the resistance as well as the voltage. So these are the four different tasks that we are going to complete today. So let's start with the with this circuit. So we need 3 resistors. Let's go to the LTSpice, open the schematic, bring in the resistor R1, R2, and R3 over here, and I'll put the load resistance over here. I'll need a voltage source of 24 volts. Right? Okay, here's the voltage source. Okay, so now I'll bring F3, I'll bring the wires, I'll connect the wires. So okay, that's okay. And then this is what our circuit is. So we have a Y connected circuit, and we have a load resistance voltage sources here, and ground. So let's bring the ground here, F3, and let's connect the ground. Please make sure that you should take care of the naming. So the net labels are very important in this lab. For example, I would love to let me set the values first. So R1 is 8 ohm, and then we have 4 ohm and 6 ohm. So we have this one is 4, this one is 6 ohm, this is 24. Yes, 24 volts. Okay, and my load resistance is 1 ohm. Once the circuit is connected, I would like to change the name of this one into the load resistance, and then I'll bring the net label. Sorry, I'll keep on forgetting the F4 will bring the net label. So I will name it as voltage cross the load resistance. So I'm going to bring this one here, and this one is an input voltage. I'll also make sure that as per the convention, I am connecting, I'm naming my Y connected network as R1, R2, R3. If it was a delta connected circuit, I would definitely change them into RA, RB, RC so as to stay consistent with what we are learning within the class. So once that is done, nothing's missing. So let's simulate our circuit. I'll go and simulate the circuit. I'll say stop time is 2 seconds. Start saving data at 0 point. Once done, okay, I will check the voltage across my resistance, load resistance. So my VL is 827.6 millivolts. Current through the resistor is 827.6 milliamps. So one more thing, one very important thing, when we are dealing with a complex circuit and we have to find the resistance, the voltage across a resistor. For example, if there were like 4 to 5 resistors connected here in another network, and we would like to find the voltage across an individual resistor, and all you have to do is to bring the scope. For example, I'll bring the scope here. I'll click the mouse. I'll keep clicking the mouse. I won't leave it. And then I'll bring it to the next point. The next point, and then it will give me the voltage across this resistor. Alright? So if I'm going to find the voltage across R2, then this is meaningless. If I just put this thing as, if I'm probing the voltage here, then this is giving me the voltage which is at these 2 points. But if I'm interested in finding the voltage across R2, I'll have to click here and then I'll bring it over here. And you see, you will see actually immediately that this voltage is a different point. Alright. Similarly, the voltage across R1 is this one. Alright. So that's also very important. Please make sure when I'm saying that the voltage across a resistor, it means that this is what I'm talking about. So voltage across R2, and the voltage across R3 is this one. Alright. So that was an important point, that how to find the voltage across a resistor. That's very important. Okay, so coming back to the main lab, so this is the current going through the resistance. This is the voltage across a resistor, and the power. For the power, you press the Alt button, the Alt key on your keyboard. Your probe changes into a thermometer thingy, and then click it, and then you get the power, which is 684.899 milliwatts, somewhere here. If you're looking to find the power exactly, you have to bring the cursors. Just bring in the cursors. You click in here, and then the cursors start moving, and this is where you start finding the power. This gives you the exact, which is 684.899 milliwatt. Similarly, if you're looking at the voltage, just click this one, and your cursor is now selected. So cursor just sticks to your value, which is highlighted here, and then starts giving you the values over the horizontal scale in time and over the vertical scale in whatever the unit is. So I'm looking for current by R1, and you see it changes into the millicurrent. That's the way we work with the cursors. Okay, delete this trace. So right now, so that's what it is. So we have found the power, the voltage, and let me also bring the current in here. Okay. So we have all these 3 values listed here. This circuit is done. Now I have already done the calculation. So actually this is the circuit, and for the conversion, I'm sticking to this convention where I always start ABC in a right clock fashion. But if you will have learned it in a different way, please use that method, and the results remain same, provided you are consistent with your calculations. So this is the way I'm calculating. So when I'm trying to convert my Y into the Delta network, then I have to find the RA, RB, and RC. I'm using these conversion formula to calculate my RA, RB, and RC. Based on that, this is just another way if I'm converting back from Delta to Y. So based on that, I have already calculated my RA, RB, and RC. So I will start wiring my circuit in this new fashion. So let's go. I'll open a new circuit. I'll bring a resistor, rotate it. I'll bring the resistor here, and the one here, and the load resistance here, and my voltage source over here. All right, so now I'll start connecting the wires. So I'll bring F3. Here. Oh, it's a little bit, okay, no problem. Doesn't matter actually. Just to make it beautiful. Anyways, it's the same wire, so it doesn't matter. My load resistance is, sorry, I'll cut the wire quickly. So my load resistance is here. I'll bring it here. Okay. Well, it looks like the wire is not connected here, so let me just fix it a bit. Okay. Okay. And okay, F3. Now it's connected. And it looked like it wasn't connected, so just to be sure. Okay, now as I said, I have to be consistent, so my nodes will be A, B, C. So based on that, this is my resistance R A. This is my resistance R B, and this is my resistance R C. Because I named the nodes as A, B, and C, and when I say A, then the resistance opposite to it is RA, and if it is B, then the resistance opposite to this one is B. Similarly, resistance opposite to the C node is RC. And based on that, and I'm changing this resistance into RL. Now coming back, RA is 30 ohm. Once that's done, actually, then the rest becomes very easy. So we don't have to care 13 RB. I mean, where the resistance goes. So that's why I'm stressing on to stay consistent and about the naming of the resistors and the components. So RB is 17.3 ohms, 17.3, and the last one RC is 26 ohm. RL is 1 ohm. This was 24 volts, and I'll bring F4 net label as VL. Put it here. Perfect. Now I need the ground. I'll bring the ground, F3. Keep on forgetting the ground. Let's run the simulation for 2 seconds. Start setting data when it's 0. Done. Okay, here's the simulation. So let's see the voltage across the load resistance. It is 827.6 millivolts, which is exactly here. As you see the things here, it's 827.6 millivolts. And the current is 827.6, which is 827.6. You can see here 827.6. And then the power through the resistance is 684.8 8 something, and which is 684.899 something. So our conversions work. So if we stick with the convention, then our circuit equivalency works. These two are done. Let's move to the third circuit. Let's change it into the Thevenin equivalent. I'm not going to go into the details. Actually, the details will be very simple because this is a very simple Y connection, and if you start connecting this circuit, you bring this node in here, and this is the load resistance. You know there's no current flowing through this resistor, and actually this R1 and R3 forms a very simple voltage divider, and you can quickly find out the Thevenin voltage. It will be very simple to find the Thevenin voltage, and then the Thevenin resistance, where two resistors are in parallel with one of the resistor. It's very simple to calculate the Thevenin equivalent of this resistor, of this network. Once that is done, I have already found them. The Thevenin equivalent, the Thevenin voltage is 8 volts. The Thevenin resistance is 8.67 ohms. Let me bring in a new circuit. So I'll bring a voltage source, which is a Thevenin voltage source. I'll bring the resistance. This is the resistance, will be Thevenin resistance, and the load resistance. And I'll bring the ground here. Start wiring the circuit. F3. Okay. I'll name this as RTH, and this one as VTH. This one, so okay, I'll put one ohm value, and then I'll say this is my load resistance. Current voltage is 8 volts. So this is pre-calculated. Thevenin resistance is 8.67 ohm. I'll go with 8.67 ohm. You can easily calculate that. There's no problem with that. Let's run the simulation for 2 seconds. Actually, even 1 second is okay. I'm just, I have made myself a habit of putting the rubber tool. Okay. So this is the circuit here. Let's see the voltage. So as you see, the voltage at node 002, which is here, I'll call it B. Okay. Run the simulation again. So run the simulation again, and this is my voltage across load is 827.2 millivolts, which is close to 827.6 millivolts. And then the current through the resistance is 827.4 milliamps, which is again equivalent somewhere close to what we are. The difference is 2 minus. It's very, very small difference. And then finally the power. The power is 684.4 milliwatts, which is again very close to what we are looking at. So this was our Norton equivalent circuit, and we see everything is consistent. Let's find the last one, the Norton equivalent. For the Norton equivalent, the current source is supplying 0.923 amps, and once you have found these things, you can quickly find these values. And the Norton resistance will be equivalent to Thevenin resistance in this, so we will just put these values. Let's bring in R and load resistance. Let me bring the current source, control right. Okay, and the ground, and the wires. Okay. Current is 0.923 amps and 8.67. 8.67 ohm. Load resistance is 1 ohm. Okay, run the simulation for 2 seconds till okay. When I try to find V underscore L, bring it over here. Okay, let me run the simulation again. So look at my, is there something wrong? Okay, just let me close a few of these circuits. No, I don't want to save. I don't want to save. Oh, must be something wrong with the. Why it's not here. Next. Something's gone wrong. It's not responding. Okay. I think there's a problem with the ground not properly connected. So I will connect the ground. Okay. I think that was the issue. Okay, and now I'll just bring in this one. So my voltage now is 826, 27.6 millivolts, and again, just to confirm here, 827.3, something like that, 827.3. And then the current through the resistance is 827.6 milliamps, while here, okay, the current here is 827.4 milliamps, somewhere around that point. And finally the power is 684.8, and for this 684.4 milliwatts, 684.8 milliwatts. Okay, and with that we conclude the lab session. So please make sure the circuits that I'm giving, follow the instructions. All you have to do is to do the same things. You don't have to show the calculations. You can do the conversions, and just once you're done with those conversions, just start building your circuit, and the screenshots should go into your lab report. While you're taking the screenshots, please make sure you click on the tools and then copy your bitmap clipboard or write image to an EMF file. You can choose both of these. Copy bitmap to your clipboard is one of the good ways. Or you can always go and say print preview. And within the print preview, you can get a very good, and you just print it in a high resolution PostScript file, and then you can attach it to the lab. I hope you guys have learned something today. If you have questions, please let me know. Bye.